So I'm going to start off here, introduce our next speaker. Charlie Cigrand is with the USGS with the title Physical Scientist. He made my life really easy, gave me a very short bio, so we'll have him give us a little bit of background on what he does as a physical scientist at the USGS and the work that he performs. He's been with the USGS since 2015 and specializes in surface water modeling. So rainfall, runoff type of modeling. But he wears many hats, goes out with a field sampling crew, does data collection, and does some of the GPS surveying for his own projects. So a great wealth of understanding the terrain surface and incorporating everything into his models. So now we're going to switch a little bit, and we're still going to talk about flood inundation models and mapping. But now we're going to look at how a watershed reacts, how it performs during the events, and then also simulate some flood mitigation practices and take home some message what we have for different practices and how that impacts flooding for a small community over by Iowa City. So, Charlie.
Hi there. So my project is on the development of flood inundation modeling for mapping and simulating flood mitigation practices in the West Branch Wapsinonoc Creek Basin, which is located in West Branch, Iowa. So here's kind of an aerial of the watershed. It's a 8.5 square mile watershed. This is the town of West Branch, so they're a cooperator in the project, and then also the National Park Service is another cooperator, and they're located right here. It's kind of an important area of interest because these creeks form into each other right here. Whoops. Right in conjunction of town, and also the park, which houses the Herbert Hoover's childhood home, some other historical buildings from his era, the presidential library, and also the visitor center, and all this is located right along the banks of Hoover Creek. So the problem they're having is these flashing flooding events. And they're trying to control these 5-year, 10-year, and 25-year events from flooding the structures in town and in the park. So we do, the USGS, we install gauges, stream gauges, and also precipitation gauges. So these are the areas that we've installed the gauges. We have a discharge gauge here in the park, a discharge gauge on the northern end of town, and also we installed a stage-only gauge where a tributary comes into the Wapsinonoc Creek, and also on the main stem on the upper part here, and then also a precipitation gauge up here, one on the northwest part of the watershed, and then there's another one located in Hoover Park. We recently took this precip gauge down because we're getting the same data as from this gauge since they're so close to each other. This is just a quick picture of showing the install of some of the gauges. This is the gauge on College Street on the north side of town. It's, like I said, it's a stage gauge and also a discharge gauge. This is the gauges that we installed on the northern part of the watershed, the stage-only gauges. And also, this is what our precip gauges look like. So, the data that these gauges collect, I need to build a hydraulic model. I need the precipitation gauges in a different way than normal. You might think about a rain event. Normally, you think about a rain event with the total precipitation, say it's you got 5 inches of rain. Well, I need to know how much rain you got in time steps. So our gauges will tell you in 15-minute time steps how much rainfall you're receiving, so you know how much to apply under your watershed throughout time. And then also, I need to know the discharge information so you can calibrate your hydraulic model so you get the right amount of runoff to match whatever discharges we're getting at these gauges. So the first model I built is the hydraulic model, HEC-HMS, and it consisted of the entire watershed here, which I divided up into 14 subbasins, or miniature watersheds within this watershed, and then the creeks were divided up into 8 river reaches. Some of the parameters used in this program for loss method, I use the SCS curve number, which is your runoff value. Transform method, I use the Clark unit hydrograph, base flow method, recession, and the routing method, Muscombe-Kunge. So to produce a runoff model, you need to replicate these rain events. So we've had this, our gauge in Hoover Park has been there since the year 2000. So these are the highest events that we've had for discharge at that gauge. And so I used 4 of the top 5 events that we measured with that gauge to calibrate the runoff model. We also have some data from the 2 highest flows that was received at this location, but as you can see, the one was the highest flows from the 93 flood, and then there was also a flood in 1969. And these are only estimates of discharge at that location because the gauge was not installed there, so I did not use these events for calibrating the model. So you have to change some of your parameters to match the hydrograph to get your volume, your total volume coming off the watershed. You want to match your peaks of the hydrograph and also the timing of the rising and receding limbs. So this is kind of in general, what some of the parameters, what they control on the hydrograph. So my runoff curve numbers control, the amount of volume that's coming off as runoff. The time of concentration deals with the timing of the peaks and how soon or they occur. There's also a storage coefficient, which deals with your hydrograph attenuation, how much water is getting held back or expanding out in the floodplain, attenuating your hydrograph. Also, Manning's N value does the same thing. And then base flow parameter, and that has to deal with just your receding limb of the hydrograph and matching that curve. So after I calibrated to those 4 events, I averaged the parameters together to get a calibrated model that I can run any sort of design storm through. So here's an example of the values I use for the subbasins. And so I have the runoff curve number, and then it's your ARC2s, which is your antecedent runoff condition. And your ARC2s are your normal conditions, which is your soil moisture content and how much the soil can absorb for rainfall. And then your ARC3s are saturated conditions, where you're going to have the soil can't take in as much rainfall, cannot infiltrate as much, so you're going to have greater amounts of runoff. And here you can kind of see how I was able to match the hydrograph with the runoff model. The black line with the dots, that's our measured data coming from the Gage, and then the blue line that follows it, that's what the output is from the HMS model. So like I said, once I was able to calibrate to those 4 events, average the parameters, then we have a validated model. So I can then use that model and create these design storms where I get storm frequencies from the NOAA Atlas 14, which uses statistical analysis of regional rain gauges to come up with storm frequencies. And typically for a design event, we use a 24-hour duration storm. And so for this model, I modeled, five different conditions. Your 50%, 10%, 4%, 2%, and 1% frequency-based rain events, which is also the same as your 2, 10, 25, 50, and 100-year event. So these are some of the values that I got off of the Atlas 14. So a 2-year event is about 3 inches of rain. Then all the way up to a 100-year event is 7.35 inches. So then there's a storm. You can build these rain events in HMS, and it'll create a hydrograph, as you can see right here. So that's what it's plugging into the model for precipitation. And as you can see, it's very typical of a storm in the Midwest, where most of the rain you're going to get for a 24-hour storm is going to happen within an hour. So you design these events to where you're getting majority of your rain in a 15 or 30-minute time step, and then it extrapolates from there to create your hydrograph. So for just for comparison reasons, I came up with the discharges from running these events. This would be your 2-year, 5, 10, 25, 50, 100-year event. And so this is a discharge that I'm getting off of those rain events, running your normal soil moisture conditions, your ARC2s. And this is just a comparison of your flood frequency discharges that uses, statistics off of the Gage to come up with frequency numbers. So this just shows that, your 2-year storm doesn't equal your 2-year flood event necessarily. It just all depends on your antecedent soil conditions and how much runoff you're going to have. You can have 5 inches of precipitation, and the ground, you could have dry conditions where the ground absorbs the majority of it, and you're not going to get a high event. Whereas if you have, saturated ground and you get a 2-inch rain event, you can get high flows off of that. So once the runoff model was calibrated and I was able to produce those design storm events, I moved on to the hydraulic model, which I used HEC-RAS 5.0. So this model contains the six different streams and its minor tributaries that come up here. Also, it equated to 10.3 miles of streams, which we had to go and survey, get cross sections every 200 to 500 feet or so for this whole stretch. Also, so there are 22 bridges and culverts located in this watershed that were modeled that we also had to survey. And then just building the model, I incorporated 8 2D or storage areas and 7 lateral and inline structures. So first step for once you have the model, hydraulic model built, is calibrating it just like the HMS model. And what I used was, so they had an event in June of 2014 where they surveyed in high water marks throughout the watershed in town. And this kind of shows the locations where they got the high water marks. This is overlaid on top of the FEMA flood map. So I can use these high water marks at their locations on the stream bed, and I plotted those up here. I don't know how well you guys can see it, but it's these black dots on top of this profile. So that's the high water marks for that profile of stream for this event. So I run the event, and then you try to match what these high water marks are throughout the stream. And that's dealing with adjusting your manning and values, your ineffective flow, and any sort of other parameters that you need to adjust to get your water levels where you need them for that event. There's also some site-specific events that happened during some of these storms. So this June 2014 event, there's a triple box culvert on the I-80, on Interstate I-80. Well, I guess this left culvert was completely blocked with trees and debris from the high flows, and they had to use a bulldozer to clear this culvert back out. It's like a 12 by 12 culvert, just to clear it out because it just got lodged with debris. So during this event, this left culvert was blocked. And when I initially ran the model, it wasn't matching these high water marks that I have just upstream. This is the I-80 bridge or triple culvert. And I wasn't getting the water level up to that elevation until I was told by city officials that that left culvert was blocked. So I ended up blocking it 50%, allowing some of the water through, and I was able to match the profile of the high water marks upstream from the I-80 bridge. Also, there's 4 corrugated culverts on the northern end of town on Hoover Creek, and one of these culverts was blocked here. You can see in the picture from a door, just a regular door from a house. Somehow got into the stream and blocked this culvert during the high water event. So I ended up blocking the flow to this culvert during this event, and it brought up the water level a foot from these culverts and affected the water level to the immediate area upstream from here. I mean, there was only 3 houses, but I was able to, there was a high water mark there just from a picture that I was able to match by just blocking this culvert. So it kind of shows you just on a case-by-case basis what can happen and how something small can affect how the watershed drains. And also, there's this Downey St Bridge on the Hoover Creek that had elevated levels and backwater behind it. And I had to adjust the channel, Manning's End in the channel from 0.06 to 0.11 just to get the water level up high enough behind the bridge. So these are some of the areas of improvement for conveyance. So this is the Downey St Bridge. You can see the backwater that builds up behind that. This is an old railroad embankment that cuts through town where they removed the bridge a couple of years ago, or in the 90s, but the embankment is still there, so it's constricting the floodplain. And then also there's a bridge right below that, an old truss bridge that they use to get access to their sewer plant that they no longer need because they have a better way to get there. This shows the Downey St Bridge and why there's a backwater effect. It's very constricted. You have a very deep deck, and also there's pipes that come across the stream bed, and they're elevated above the water surface, and some fence posts that kind of hold them in place. So all this is restricting flow when you have high flow coming through, and that could be, you know, the cause of the backwater effect you're getting behind this bridge. This is the railroad embankment that cuts through town, and you can see how it is cutting off the floodplain and why they're getting a backwater effect from that. And this is just the old truss bridge that they no longer use, so it's if they're not using it, they can take it out and improve conveyance. They also have utilized measures to attenuate the flood wave. They built the retention structure on the upper end of the Hoover Creek. And so this is that structure. It has a drainage area of 0.5 square miles, and it has a capacity of 45 acre feet. And this is kind of what it does on a runoff model. This is how it attenuates or holds back the high flows. You know, it's receiving, this was a April 2013 event. It was receiving 250 CFS at one time at its peak, but only had an outflow of around 60 CFS, so that kind of shows how that can attenuate. So for my design, I designed two more of these structures on the upper ends of the Wapsinonoc Creek. This is the one on the Hoover Creek that is already in place. And I kept around the same parameters or same design. I wanted to keep it under 1 square mile, under a certain storage capacity, under 50 acre feet storage capacity, just so you're on that lower tier of dam regulations. And then it's also has similar effect, these design ones on the Wapsinonoc as these two, as the one on the Hoover, because the Wapsinonoc watershed is, well, the Hoover watershed is about 60% as big as the Wapsinonoc. So these are some, once I ran the events with these frequency storms with the retention structures, these are some of the results. The red line is with the retention structures, and then the blue lines show just the existing conditions. So this is the effects that you get through town on this reach. As you can see, it lowers the water surface for a great deal for these smaller events, the 5 years, 10-year, and 25-year events, which is what they're trying to control, but it has less effect on these larger events, the 50 and 100-year, because it's running out of storage. It can't hold back enough water during these events, and these structures are using their emergency spillways. So this is after running the channel modification conditions, where I opened up the old railroad embankment and took out the sewer bridge that's just downstream from that. As you can see, it improves conveyance and lowers the water surface elevations, especially once you get closer to the embankment. But you only have that effect so far upstream, so there's another control at this College Street Bridge, which is on the north side of town, on the outskirts of town, but you're still getting this effect throughout town, which is what the city wants. So this is with the channel modifications and the retention structures. And as you can see, it basically takes a whatever storm event down to the next level. So it's, this second red line would be your 10-year event, but it's taking it down to a 5-year storm, or it's taking a 25-year event down to a 10 and all the way up. So you can see the improvements that can be made if the city chooses to use all these scenarios on this watershed. This is the same thing on Hoover Creek. Similar results until you get to this Downey St Bridge, which there's another project at HER Engineering. They're designing some bridge designs for this bridge, and then possibly an off-channel detention basin upstream from here. So, but I'm waiting to hear back from the park, who is their cooperator, on which designs they want to use. So I haven't incorporated into the model yet. Same thing. This is what the channel modification does to Hoover Creek, and it has some effect until you get all the way up to this Downey St Bridge. But again, there's going to be modifications to that bridge and upstream from there, so I'm just waiting to get those designs to plug that into the model. And this is with the channel modifications and retention structure. And then this is just showing, you know, the change in water elevations for, I just picked 2 different locations in the watershed. This is the visitor center for the park, which is located near this Downey St Bridge, and then also a fire station that's located near the railroad embankment. So as you can see, has great effect on the smaller storm events. This is, you know, the deviation you have from using these plans towards the existing conditions, and it's, you know, it's dropping water levels 3/4 of a feet for these events here, utilizing your channel modifications and storage designs. So next steps for this project, because it's ongoing, is to incorporate the scenarios or designs that are chosen from for the Hoover Creek that's being designed from HDR, and then also model any other flood mitigation practices they might want to use a side channel or off channel detention structure, and more located near to West Branch that will, you know, attenuate more of the flood wave than a structure that's all the way on the upper end of the watershed. And then also just incorporate some more 2D areas into the model in town where these 2 creeks, where there's the confluence of these 2 creeks and they share the same floodplain. It's going to be better. You might get better results modeling it as a 2D area instead of with 1D cross sections. And that's all I got. If you guys have any questions.
We're running kind of up to our break. We've got time about 3 more minutes here before the break starts. So is there questions for Charlie on the presentation in West Branch? Yeah.
Which was gauge is cost, either a rain gauge or a stage gauge?
Repeat the question.
So he wants to know how much a gauge costs, a rain gauge or precip gauge. Precip gauges, I mean, you're going to have to, I can give you a ballpark. A precip gauge is right around $1,800 a year, and our stage gauges are between $2,000 and $3,000 a year. I think it's closer to 2, but I'm not 100% sure on that. You'd have to contact our office and talk to our field team, which run the gauges.
Yeah, one more back there.
Are you doing a floodwave analysis as part of the XRS?
Like a flood plain or?
Floodwave.
Oh. No, because that was already produced. There was a study done in 2012 that already produced the flood mapping for the city. So unless any changes are made from any structures that they put in place, that won't be done. I'm just
Back from the DNR, we were doing a physical map revision, but when we found out that HDR was in there, represented the National Park Service, and then you were in there.
Yep, so if those, once they do those changes, and if they decide on any of these scenarios, it's gonna change the hydraulics of this watershed through town, so I'm sure that will be revisited and we'll redefine the floodway for that area. So, yep. All right, thanks, guys.
Great. Thanks, Charlie. Okay, so the program agenda has us on a break till 2:45. I believe refreshments will be out, and posters are on the second floor if you wish